A journey through time and space. Have you ever wondered what our sun looked like when it was just a fledgling star billions of years ago? Imagine witnessing the chaotic birth of a celestial behemoth, the forces at work, the intense energy being released. For the first time, thanks to the incredible capabilities of the James Webb Space Telescope, JWST, we can now look back in time and see our star in a whole new light. JWST's latest discovery offers fascinating insights into the youthful stages of stars, shedding light on the major processes that may have taken place in our sun's early years. Have we solved one of the universe's greatest mysteries? What secrets are still waiting for us in the universe? The James Webb Space Telescope is a perfect example of the extraordinary advances made possible by cutting-edge technologies. Since its launch, space exploration has progressed at a breakneck pace. With its latest mission, JWST once again demonstrates its unparalleled ability to penetrate the secrets of the universe. One of his most recent triumphs involved photographing an object called HH211, with unprecedented brightness. HH211 is a Herbig-Haro object, an extremely young star that is advanced enough to shoot powerful jets into space and begin dynamically shaping its environment. This object has provided a wealth of valuable information about the youth of stars and, by extension, the youth of our Sun. Herbig-Haro objects are among the most remarkable astrophysical phenomena in young star-forming regions. They consist of narrow jets of gas ejected by newly formed stars, which are propelled into the surrounding interstellar space at high speeds. These jets collide with surrounding gas and dust, creating spectacular emissions. Discovered in the 1950s by astronomers George Herbig and Guillermo Haro, these objects first came to attention because of their enormous emissions. Long before the JWST era, the energetic jets emanating from the center of a young star were known to be extremely violent and energetic. It turns out that young stars are anything but cute and cuddly. They are certainly beautiful, but they are also incredibly powerful. It's hard to imagine the power at work here. The forces driving star formation alone are enormous, and even in the first billion years, things get hot around a young star. It takes hundreds of millions of years for a star to shine as steadily and peacefully as our Sun. The most recently observed object is the Herbig-Haro object HH211, located in an active star-forming region in the constellation Perseus, about 1,000 light-years from Earth. HH211 is particularly interesting because it is one of the youngest and closest examples of these objects, making it a perfect field of study to explore the physics of star formation in detail. The discovery also gives us breathtaking views of the dynamic processes that may have taken place in the early stages of our Sun's life. JWST has imaged the Herbig-Haro object HH211 with unprecedented precision, revealing even more fascinating information. For the first time, it has been possible to see that a binary star can even form at the center of HH211. The image shows two high-energy jets emanating from a central point. These jets are enriched in molecules such as carbon monoxide and silicon monoxide, and they provide evidence of high-energy dynamics inside the star and its immediate environment. The detection of molecular hydrogen in the jets was a big surprise and now provides a completely new picture of the chemical composition and thermodynamic conditions in the early stages of star formation. In the accretion disk surrounding the young star, other objects such as planets and moons can form. However, the intense bombardment of the disk by powerful gas streams may make it more difficult to form stable objects. Interestingly, the JWST study also found that HH211's jets are slower than those of many other Herbig-Haro objects. This slower speed may indicate that the star is in a very early stage of its development, or that the processes in this young system are generally less turbulent than those in other stellar nurseries. The ability to observe such fundamental cosmic processes at short distances and with high precision represents a significant advance in astronomy. It will lead to ever more exciting discoveries in the future. Observing the birthplaces of new stars also provides insight into how ionized gases and plasma interact. The energetic jets hitting the surrounding cold interstellar medium create bright shock fronts that serve as visual boundaries of young star systems. The first evaporations of a star are comparable to the protective envelope of our Sun's heliosphere. On the JWST science mission, scientists are excited about the new possibilities. JWST is equipped with many advanced scientific instruments. Highlights include the near-infrared camera, near-infrared spectrometer, mid-infrared instrument, fine-guided sensor/near-infrared imager, and slitless spectrometer. These instruments can detect even the most subtle light from very young and distant objects that the naked eye could never see. Using infrared technology, astronomers can now peer through dust clouds to see previously hidden corners of the universe and gain direct insight into young stars and their formation regions, which are often hidden behind dense dust shells. Thanks to the high sensitivity of JWST, astronomers and space enthusiasts can enjoy a level of detail never before achieved in the history of astronomy. JWST can not only image these delicate light signals, but also analyze them. Never before have scientists been able to observe the giant jets of Herbig-Haro objects in such detail. Precise analysis provides data on the motion and temperature of the gas as well as detailed information on all the chemical elements and molecules involved. Herbig-Haro objects, typical of active star-forming regions such as the Orion Nebula or the Perseus constellation, are important objects for studying chemical processes in space. These regions are rich in gas and dust and provide optimal conditions for star formation. Stars form from the condensation of these accumulations of matter under the influence of enormous forces. The jets emitted by young stars, traveling through space at several hundred kilometers per second, are just one part of the dynamic processes that take place during star formation. As these jets hit the surrounding medium, they heat it up and create the characteristic arcs and knots of light that can be seen in our telescopes. In this colorful spectacle, not only are enormous physical forces at work, but also a fireworks display of elements, as well as electric and magnetic forces. The fascinating observations show how the jets interact with the surrounding matter, helping to shape the cloud from which the star forms. Each jet and each color gives JWST, and therefore scientists, important clues about exactly what is going on here. Observing these processes directly and at their early stages is like having a direct look at the blueprint of a star. If we understand how matter is incorporated into a stellar disk, how the final mass of a star is determined, and what elements and gases are involved, we can draw important conclusions about the forces at work. This helps us understand the entire process of matter formation in the universe. Enormous energy emissions and magnetic forces are at work. Although we can clearly imagine star formation as one of the most energetic processes in the universe, it is difficult to imagine that such a young star can create winds hundreds of light-years long and blow them into space. The jets from Herbig-Haro objects may be the direct remnants of the enormous angular momentum that caused the central dust disks to begin rotating and condensing. The young star may use the jets to expel unwanted forces, and the released energy may fuel the maturation process within the cloud of gas and dust at IN stellar systems. Jets have so far only been observed in young, actively forming stars. However, we also know that very old galaxies in the universe generate violent jets at their active centers. Some of these galactic winds extend far beyond their home galaxies. The winds are also capable of dispersing large amounts of matter, ultimately affecting the mass of the star and the environment surrounding the star formation region. The released matter and energy would then lead to the birth of other stars or other dynamos in the universe. Let's consider for a moment the role of magnetic structures around a young star. Magnetic fields are essential for controlling the accretion process, in which the star attracts gas and dust from the surrounding disk, and they also influence the direction of the jets. Magnetic fields are not only important in the vicinity of young stars but are also present throughout the universe. These invisible forces direct the trajectories of charged particles and influence the shape and evolution of entire stellar systems. In our solar system, the magnetic force transmitted by the Sun's magnetic field is essential for maintaining the heliosphere, the bubble that protects the entire solar system from harmful cosmic rays and particles from interstellar space. The Sun itself generates a complex and variable magnetic field that determines the order of our planetary system, conditions Earth's climate, and controls space weather. Sunspots, solar coronae, and coronal mass ejections are manifestations of the Sun's magnetic activity. As you may know, such events sometimes have a significant impact on the operation of satellites and communication systems on Earth, and they produce auroras. The study of magnetic fields in young star systems like HH211 is an exciting and still in its infancy area of research. Understanding star formation in distant regions also gives us a glimpse into the history of our Sun. Our star is 4.5 billion years old and has undergone many changes since its birth in a disk of dust and gas. The beginning of the system also determined how the planets formed: mighty Jupiter, rocky planets including our Earth, other gas giants, and small planets like Mercury and Pluto. All of them were present in one way or another at the beginning of the system, or very specific circumstances helped shape the formation of the planets and thus the cosmic environment of our home. The more we know about this subject, the more we will be able to understand how our solar system formed, and the more we will know about the general creative processes in the universe. Once we decipher the formula for forming stars and thus matter, we will be closer to understanding the universe and perhaps even finding something like a cosmic blueprint. Pillar.so Stay tuned and look forward to many more videos as we continue to explore these fascinating discoveries.